Hello students, welcome to IMS GATE Academy Guest Booster Session for Manufacturing Part 3. Okay, so myself, I'm Vijay Kumar. I finished my PhD and pursued MTech in NIT Suatkal and All India GATE 347 ranker. Now, so far we had been discussed about some basic manufacturing process such as casting, welding, metal forming process, as well as metal cutting also we have finished. Now today's talk is machine tool operations and also metrology and advanced machining process such as CNC and non-conventional machining process and material science questions I am going to cover. So the questions which I have collected definitely enhance your confidence levels. Okay, so don't worry about that. You just follow the instructions and follow the lecture so that you will be able to get some confidence on the topics which you have already prepared. Okay, thank you all. Let's go for the session. Yeah, Abhinandan Prasad, not I have solved just now. You just have a look on that. I posted due to my busy, I could not able to do that. Now I have done that. Have a look on that. Okay. Now let us go to start the session. Machine tool operations. Right. Now in that first question. One minute, guys. Delhi PPT మారిపోయింది. Welcome back, guys. Yep. Now let us go for the session. The first question is, have a look on this question, guys, once. Have a look on this question. Yeah, Jayaprakash, thank you very much. Good evening to you. Okay, have a look on this question. And actually, the beauty of question here is that actually in machine tool operations, we always focused on gate point of view, machining time calculations as well as the metal removal rate. Okay, to that purpose here I have collected machining time calculation for this job. Okay, actually for turning or for some other machine tool like lathe operations, we used to calculate the machining time calculations. Okay, but here I have inserted 5 operations in one job so that you will be able to get some tricky in the question, so that will be mitigate your doubts and as well as approach towards the problem. Okay, so hope you understand. So now let us have a look on that question. Have a look on this question, guys. Then we will move forward. Right. So a mild steel bar 100 mm long and 38 mm diameter is turned to 35 mm dia and was again turned to diameter of 32 mm overall length of 40 mm as shown in figure. Okay. The bar was machined at both ends to give a chamfering of 45 degrees by 5 or 5 radius mm. After facing, calculate the machining time assuming cutting speed is 60 meters per minute and feed rate is 0.4 mm per revolution and depth of cut is not exceeded to 3 mm and in any operation. So here totally turning operation is mentioned and chamfering operation is mentioned and also facing operation we have to done. For this all operations, how much machining time we have to calculate, guys. Okay, now let's have a look on this data. A mild steel bar of length of the job is 100 mm, length of the job is 100 mm and 38 mm is the diameter. So actually it is a machined part. Before it is machining, it is a length is 100 mm, diameter is 38 mm. Now it is turned to 35 mm. So after turning operation, 38 mm is reduced to 35 mm of diameter. Next, again it was turned to diameter of 32 mm. See, so 32 mm diameter. Again it is turned to 32 mm diameter in a overall length of 40 mm. In this 40 mm length, 32 mm diameter is reduced. Okay, so length of the job for the second operation as shown in figure. The bar was machined at both ends. Chamfering of this much chamfering has been done. So here it is a chamfering operation. Okay, this is chamfering. All right, guys, chamfering operation. And calculate the machining time assuming cutting speed of 60 meters per minute and feed is for 0.4 mm per revolution and depth of cut is not exceeded to 3 mm. Clear, everybody? So hope you understand. Okay, so thank you Pavitra, thank you very much. Okay, yeah, thank you Pavitra. Right, next is now let us go for given data and then we will solve the step by step. First we will calculate the machining time for the job of 38 mm to 35 mm. Okay, right. Next, first I'll write given data. So what is the cutting speed? Cutting speed is equal to VC. We consider it is how much it is given? 60 meters per minute is given. Okay, now and then next is feed is given. Feed F, that is equal to 0.4 mm per revolution. Okay, next is depth of cut. Depth of cut is equal to, it is 3 mm is given. And after that diameter of the job, initial diameter of the job, dia of workpiece. Dia of workpiece is 38 mm. Okay, this is what given data. Now let us calculate that first step. In the first step. In the first step, what I'm going to do is, so 30 mm diameter is reduced to, 38 mm diameter is reduced to 35 mm. For this, how much time it will take? Machining time for reducing the 38 mm diameter into 35 mm in a 100 mm length, I'm going to find out the machining time. That is the first step. In the second step, what happened? In the second step, I'm going to calculate the machining time of this block. That means reducing 35 mm to 32 mm in a 40 mm length. After that, I calculate that chamfering time. After that, facing I'll calculate. After that, I'll calculate chamfering time. If I add all those, so that I'll get total machining time for this particular job. Clear, everybody? Right? In the first step, what I'm going to do? So time required for reducing 38 mm diameter 38 mm to diameter 35 mm. 1 minute. 35 mm in a in a 100 mm length. In a 100 mm length. This is what I am going to do. Alright guys, okay. Time required for reducing the diameter 38 mm to 35 mm in a 100 mm length I am going to find. Clear everybody? Right. Now let us take that. Time for machining or time for cut. Time for machining or time for cut, that is equal to, it is L by Fn is a basic formula, right? So length of the job is how much? Length of the job is how much? 100 mm. In a 100 mm length, I am going to reduce 38 mm to 35 mm. That is why length of the job is 100 mm. Okay. Now here length of the job is 100 mm, and we don't know F. We know 0.4 mm per revolution. F is equal to, given in the problem, 0.4 mm per revolution, right? Now what is N? N we don't know, isn't it guys? For that N, so we have a formula that N equal to, it is 1000 V is divided by pi d, right? So now 1000 into V. So how much V given in the problem? V is given 60 meters per minute. So that is why I multiplied with 1000, so that it is become 60 mm per minute. Now pi d. So now which d we have to consider? So here 38 mm has to be reduced to 35 mm, isn't it guys? Yes. Now for that purpose, here what is the diameter which is maximum diameter which is exposed for the machining, that we have to consider while calculating the RPM. Okay, while calculating the RPM, you are supposed to select the maximum diameter which is exposed for the machining operation. All right guys. Now for that maximum diameter is 38. Okay, so I'll get my RPM is 503 RPM. 503 RPM. Now let us calculate that machining time. Machining time is equal to, so first step na T1 I'll take. So now T1 here also you take T1, that is L by F into N. Now where L is 100 and divided by F is 0.4 and N is 503. So that you are going to get machining time of 0.5 minutes. 0.5 minutes. 0.50 minutes you are going to get for the first step. Isn't it guys? Okay. Now these are the first step. In the next step, so what we have calculated, for 38 mm diameter of the workpiece to reduce to 35 mm in a 100 mm length, we have calculated time. Now next our step is, we have to calculate the machining time for reducing the diameter 35 mm into 32 mm in a 40 mm length. That is what our second step. So calculate the machining time for that. Now let us go for second step. In the second step, what I am going to do? Okay, so time required for reducing diameter 35 mm to diameter of 32 mm in a 40 mm length. In a 40 mm length. 40 mm length. Okay. Now here, so time for machining. Time for machining is equal to T2 we say. Second step na T2 we say. Now time for machining is equal to, it is L by F dot N. L by F dot N. L by F dot N. Clear everybody? Now from here L by F dot N. Now here length of the job, obviously it is 40. Okay. Now when is going to be changed? Why? Because diameter here 35 mm is going to be exposed for the machining. Okay. Because already we have done 38 to 35. Now 35 is reduced to 32. That is why your maximum diameter is 35. Okay. Right. Now let us go for calculating the N. N equal to, it is again 1000 V into pi d. So where d is equal to 35, 1000 into 60 is divided by pi into 35. Okay, so from there I am going to get my RPM is equal to 545 RPM. 545 RPM. Okay, now I know that L, I know that F, I know that N. Now let us substitute all these values. L equal to 40 and N is equal to 0, F equal to 0.4 and N equal to it is 545, such that you are going to get it is 0.18 minutes. 0.18 minutes as a T2. Okay, now we have calculated. Yeah, thank you, Sagar, thank you very much. Yeah, thank you very much, right? Now let us go for third step. Third step is facing at both ends. Facing at both ends. Facing at both ends. Now my job of the workpiece is here. It is, so here it is a 35 now. 35 mm is a diameter. Okay. Now facing means my tool will travel from here to center of the workpiece. So that facing is going to be done. So this is rotating in here. It will workpieces will rotate like this, and then this workpiece, the tool is going to be moved towards the workpiece such that facing is going to be happen. Now here length of the tool is half of the diameter of the tool. Okay. Now facing at both ends. Time for facing. Time for facing. Time for facing. That is equal to T3 we say, and that is equal to, it is again L by F dot N only. Now where L is equal to, it is 35 by 2, that is 17.5. Okay. Now F is 0.4 as already we know now. 0.4 mm per revolution. Okay. Now next is N is equal to 545 only we have to consider, because 35 mm diameter only na. So for 35 mm diameter we have calculated already speed. So that is 545 RPM. Okay. Now let us go for T3. T3 is equal to, it is 17.5 is divided by 0.4 into 545. That is equal to, you are going to get 0.08 minutes. 0.08 minutes. But it is, guys, do remember, it is a facing operation at one end. So this end also we have to do the facing operation now. For that purpose, what we have to do now? So we have to multiply this 2. Okay, right. So time required for facing both ends. Time required for facing both ends. Facing both ends. Okay, right. Now I just multiply this fellow with a 2. So time required for facing at one end is 0.16 minutes. All right. Now we have done turning, facing also. 2 turning operations. So first turning operation is 38 to 35, and second turning operation is, this is the second turning operation, and it's a first turning operation, and then facing operation we have done. Now fourth is chamfering we have to do. So we have calculated machining time for 1, 2, 3, and also chamfering also we have to calculate the machining time. So let me calculate the machining time for the chamfering. But do remember, guys, chamfering is done at both ends. So this end and this end. So one side we will calculate, and next side we are going to multiply with the 2, so that we are going to calculate the chamfering time. Okay, right. Now let us go for time required for chamfering. Fourth step is time required for chamfering. Chamfering at one end. Now here tool travel. So now time for T4 equal to, it is L by F into N again. Okay. Now what is the tool travel here? What is the tool travel here for chamfering? We have to decide how much the tool is going to be travel. that is given in the problem na, 5 mm, 5 mm. So radius of the chamfering is 5 mm. So that this become as a chamfering radius equal to 2 length travel. All right. Right. Now let us go for that. Right. Now here L equal to 5 and this is 0.4 and we'll consider it as a 545 only. Why? Because diameter of the workpiece is not changed from the 35. That is the reason why here I am considering my RPM equal to 545 only. So whenever diameter is not changed, then RPM is remains same. Okay. From there I can calculate this. Yeah, 0.02 minutes will come. 0.02 minutes will come, right? But time required for chamfering both ends. Time required for chamfering both ends. Time required for chamfering both ends. Now in that case what happened? So here chamfering at one end into multiply with the 2, 0.02, I'm sorry. Yeah, 0.02. 0.02 such that it is going to be a 0.04 minutes, right? Now total machining time for the job. Total machining time for the job. Total machining time for the job. T1 plus T2 plus T3 plus T4 equal to, you are going to get total machining time. Clear everybody guys? Okay. Hope you understand. Right. Time required for machining. Total time is equal to it is going to be a T1 plus T2 plus T3 plus T4, right? Now T1 is equal to, it is 0.50 minutes plus T2 is equal to, it is 0.18 and T3 is equal to 0.16 plus T4 equal to 0.04. If we add all these, now you are going to get it is 0.88 minutes. You are going to get it is 0.88 minutes. Okay guys, this is what happening here. Okay. Yeah, thank you Sati, thank you very much. Okay, right. Now see this guys, like that here the beauty of question I just remind you, summarize in a minute, that is, see here I have inserted 4 operations in one job, right? So most of the cases they will ask you in turning what is the time required for machining, like that. So if you engage this kind of typical questions, so that whatever the doubts you are having in your mind during machining time calculations for the, especially for the lathe operations, that will be mitigated. Okay, so hope you understand this question. Okay, right. Now let us go for the next question guys. Yeah, next question. Have a look on this question. Yeah. Determine the machining time for a mild steel bar 52 mm diameter down to, it is not mm, 44 mm diameter over a length of 200 mm with HSS tool. The approach length of tool is 5 mm and rough cut equals to 3 mm with a cutting velocity of 35 meters per minute and feed rate is 0.3 mm per revolution, and finishing cut equals to 1 mm, cutting velocity is 15 mm, 15 meters per minute and feed is 0.1 mm per revolution. Okay. Now have a look on this question guys, read carefully once and twice. Okay. So determine the machining time of a mild steel bar which is having diameter, 1 minute, I'll change the ink. Right. So determine the machining time for a mild steel bar of initial diameter of 52 mm to the final diameter of 44 mm. Final diameter of 44 mm over a length of 200 mm. Length of the job is 200 mm. Okay. Next, with a HSS tool, the approach length of the tool travel is 5 mm. Approach length is given 5 mm. Next, rough cut is equal to 3 mm. That means depth of cut, rough cut is 3 mm. Okay. Now with a cutting velocity of 35 meters per minute and feed is 0.3 3 mm per revolution. Okay, now next is finishing cut equal to 1 mm. That means depth of cut of finishing cut. Depth of cut of finishing cut is 1 mm. Now cutting velocity for the finishing cut is 15 meters per minute and finishing cut feed is 0.1 mm per revolution. Okay, so if you segregate the data properly and if you understand the problem properly, so that it would be very useful for you to solve this kind of question. Okay, now if you observe this kind of question, what happen now here, rough cutting and also finishing cutting is going to be takes place, isn't it guys? Rough cutting and finishing cutting is going to takes place. For rough cutting they gave some parameters, for finishing cutting they gave some parameters. That means cutting speed and feed is going to be vary for the cutting speed and cutting speed and cutting feed are going to be vary for the rough cutting as well as the finishing cutting. Okay, first we'll write that rough cutting parameters and secondly we will write that finishing cut parameters, so that it is possible to you to solve the question very easily. Clear everybody? Thank you very much. Okay, right, now for rough cutting, rough cutting, so what are the parameters given? Mild steel bar is 52 mm, initial diameter is oh my god, okay, initial diameter is 52 mm. Okay, now final diameter is, not final diameter, length of the job is 200 mm, length of the job is 200 mm. Okay, next is approach length of the tool travel, AP is equal to, it is 5 mm. Okay, next rough cut equal to 3 mm, that is D equal to 3 mm, D equal to 3 mm. Okay, next and rough cut equals to 3 mm, cutting velocity, that is for rough cut VR I'll say. So cutting velocity for the rough cut is equal to, that is 35 meters per minute, 35 meters per minute. And and feed is for rough cut, FR stands for feed for rough cut, that is equal to 0.3 mm per revolution. Yes guys, okay, this is what the data for the rough cut. Okay, similarly you write for finishing cut, okay, now finish cut is D initial is equal to, it is 46 mm. You may get doubt, sir, how it is become as a 46, I'll explain you with a small diagram. See guys, right, actually initial diameter of the workpiece is, how much it is? 52. Yes, initial diameter of the workpiece is 52. For the rough cut, depth of cut is 3 mm. For rough cut, depth of cut is 3 mm. If I gave depth of cut 3 mm for this job, then what happen? See, so 3 mm will go this side and 3 mm will go this side, isn't it guys? 3 mm top and bottom is going to be removed. Okay, yeah, thank you Gangadhar, thank you very much. Okay, right, now here what happened na? The workpiece is going to be rotated like this na. So whenever we give depth of cut of 3 mm, so it is going to be removed from the top and also bottom. So 3 mm this side, 3 mm this side, if you remove, then what happen? It is gonna be a 46 mm. This length. That is why at 46 mm finishing cut is going to be takes place. Clear everybody? Try to understand why I have taken finishing cut initial diameter is 46, because in the rough cut, because of the 3 mm depth of cut, 52 mm is reduced to 46 mm. Okay, right, now for the 46 mm finishing cut is going to be takes place. That is what you have to understand. That is a beauty and tricky in the question. Clear everybody? Right, so hope you understand. Right, now I have taken, because if the rough cut depth of cut is 3 mm, if I gave 3 mm depth of cut during turning of 52 mm, 3 mm up top side, 3 mm bottom side will gone. So 52 minus 6, so that you are going to get it is 46. Clear everybody? That is why I have taken this much. Okay, now for the rough cut, and what is given? Cutting velocity. We see for rough cut VR is equal to, it is 15 meters per minute, right? Now for speed for rough, sorry, finish cut na, let me go for that. Finish cut we are doing. Right. So we finished cut and F speed for finished cut is 0.1 mm per revolution. All right, guys, this is what happening in this one. Okay, now first we'll calculate the machining time required for the rough cut, machining time required for the finishing cut, so that we will be solving to, if we add that finishing cut time and rough cut time, so that you're going to get total machining time required for the machining operation. Clear, everybody? Right. Time required for rough cut. 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 Obviously, so we can consider it as a TR, time required for rough cut. That is equal to L by F dot N. Okay. Now, what is the length of the job here, guys? Length of the job is given 200 mm, na? 200 mm. But here, do remember, approach is also given. Approach is also given, right? Now, let us go for, right, length of the tool travel. I'll take ink again. Length of tool travel. Length of tool travel. That is equal to, L is equal to, it is L plus approach, where L is the length of the job, where L is the length of the workpiece or job. Now, where AP is the approach length of tool travel. Approach length of tool travel. Approach length of tool travel. Yes, guys, clear, everybody? Okay, right. Now from here, so length of the job 200 plus approach length 5 mm is given, na? So length of the job is 200 mm and approach length is 5 mm, right? Now from there it is gonna be a 5, so that you are going to be 205 mm. Isn't it, guys? Okay, right. Now here feed is given for the rough cut. FR is equal to 0.3 mm per revolution. 0.3 mm per revolution. Now N we have to calculate. Okay, N is equal to, it is 1000 into VR is divided by pi into D. Right. From there I can write it is, so rough cut velocity is given, na? Rough cut velocity is given, na? So rough cut velocity is 35 meters per minute. 35 meters per minute. 35 and is divided by, what is D? What is D? Initial D is 52 mm. So pi into 52, such that you are going to get your RPM is 214.24. 214.24 RPM you are going to get. Clear, everybody? Okay. Now you got N, you got F, and you got length. Now calculate the time required for rough cut. So now TR is equal to, it is 205 is divided by 0.3 into 214 only, na? Yeah, 214.24, such that you are going to get rough cut machining time is 3.18 minutes you will get. All right. Clear, everybody? Right. Now here let us go for time for finishing cut. Time for finish cut. Finishing cut. That is equal to, we'll say it is TF. That is gonna be a L by F dot N. Now here L equal to, here L equal to, again it is gonna be a 205. It is equal to, guys, 205 mm, and F is equal to F 0.1 mm per revolution. Now here you have to decide N equal to, it is 1000 V, F is divided by pi into D. Now it is 1000 into VF. VF is equal to, it is how much, guys? I gave that it is a 15. 15 is divided by pi into 46 such that n equal to, here you are going to get 103.79 rpm. 103.79 rpm you are going to get. Okay, now let us substitute all these values. 205 is divided by 0.1 into 103.79 such that you are going to get minutes of 19.7 minutes. 19.7 minutes, right? Now total machining time. Total machining time. Total machining time is equal to, it is time for rough cut plus time for finishing cut. Time for rough cut is 3.18 plus time for finishing cut is 19.75. So that you are going to get, it is 22.93 minutes you are going to get. Okay, clear everybody guys? Okay, now here, so what's happening now? Now understanding the question is important here. Okay, here two cuts are going to be takes place for during turning operation. One is a rough cut. For rough cut they have taken depth of cut is 3 mm. That is why it is going to be reduced from 52 to 46. Now 46 to 44, total we have to reduce 52 to 44, but 52 to 46 it is going to be rough cut. Now from 44 to 46 is 46 to 44 if you are reducing, that is come under finishing cut. Okay, so that is why I have calculated individually what is the time required for the rough cut, what is the time required for the finishing cut. And in the problem also they mention different process parameters for finishing cut as well as the rough cut, right? Now for rough cut the speed is given, cutting speed is given 35 meters per minute. For rough cut feed is 0.3 mm per revolution. For finishing cut, cutting speed is given 15 meters per minute. Isn't it guys? Now for finishing cut feed is 0.1 mm per revolution. Accordingly we have to calculate the machining time required for the finishing cut, machining time required for the rough cut, and then if you add that both, so that you are going to get the total time. Clear everybody? So hope you understand the question. Thank you all. Okay, right, now let us go for the next question. Right, have a look on this question related to shaper. Okay, in a minute, I'll be back in a minute. Have a look on this question. Yeah, welcome back guys. Let me read the problem. Right, now a 600 mm long and 300 mm wide flat surface of is to be machined on a shaper. Guys. Okay, so the surface, this 600 mm long and 300 mm width, this is a length and this is a width B. Flat surface is to be machined on shaper. The plate has fixed 600 mm side along the tool travel direction. Okay, tool traveling in the direction of 600 mm. Tool travel in the direction of 600 mm. Okay, if the total overall travel each end of the plate is over travel 20 mm each end. Okay, that means tool is going to be over travel in the length direction of the workpiece 20 mm that side and 20 mm this side. Okay, now and next the average cutting speed is 8 meters per minute. 8 meters per minute. The ratio of return time to cutting time is, quick return ratio is given 1:2, and then determine the time required for machining if the feed rate is 0.3 mm per stroke. If the time if the feed is 0.3 mm per stroke, now we have to calculate the machining time required for the shaper. Okay, now let me draw a simple diagram for this. Now here it is a length of the job. Here it is a length of the job, that is equal to, it is 600 mm. It is a 600 mm, guys. Okay. Now width of the workpiece is 300 mm. 300 mm. Right. Now what they said, so the tool is going to be travel in a length direction. So I'll show you the tool once here. The tool is going to be travel in a length direction. This is what your single point cutting tool, which is travel in the length direction. Okay. So this is a tool. Tool is traveling in a length direction. Okay, guys. Now from here, what happened? Na? So they said that if the total over travel each end, so this end it is going to be over travel 20 mm. This end it is going to be travel overrun 20 mm. So approach and overrun of the tool is 20 mm. Now the cutting speed is given. So cutting speed VC is equal to, it is 8 meters per minute. 8 meters per minute. Okay. Now feed is 0.3 mm per stroke. Mm per stroke. Okay. Now quick return ratio is equal to 1/2, that is equal to 0.5. Yes, guys. Now this is what the gate are given. Now for doing this machining operation, how much time it will take, that we have to calculate. Okay. Now for doing this machining time, how much time it is going to be calculated. Okay. Now we have to remove this surface. For that, how much time we require, that is how we have to calculate. Clear, everybody, guys? Okay, right. Now let us go for time for shaping. Time for shaping. Time for shaping. Time for shaping is equal to, it is a number of strokes into, minute per strokes. Minute per strokes. Okay. Now number of strokes we can calculate, it is width of the workpiece divided by F into here 1/ns. 1/ns, where ns is a number of strokes per minute. Okay. Number of strokes per minute. Strokes per minute. Okay. Now this number of strokes per minute can be calculated. It is gonna be a cutting velocity into 1000 is divided by L into 1 plus Q. This is what the formula. Okay. Now cutting velocity is given, 8 into 1000 is divided by L. So now let us decide L. So L is total this much. Okay. L equal to, it is approach plus length of the job plus overrun. Now approach is 20 plus length of the job is 600 plus overrun is also 20. So that it is gonna be a 640. It is gonna be a 640. Yes, guys. Okay, right. Now length of the job is 640 and quick return ratio 1 plus 0.5. From there it is gonna be a 8000 is divided by 640 into 1.5. So the, oh my god, 1 minute. 1.5, that is equal to number of strokes per minute. You are going to get 8.33. 8.33. Now, so let us calculate that. So time for shaping. Time for shaping. Time for shaping is equal to, it is BW by F into 1/ns. Okay. Now B, what is B, guys? What is B? B is the width of workpiece. B is the width of workpiece. Sometimes they may ask you to consider approach and overrun in the lateral direction also. That means the tool is also moving in this direction. Na? The tool not only move in the shaper, it is also move towards the width side also. Okay, right. From there, so B is 300 and it is 0.3 into 1 by number of strokes per minute. 1 minute. Just now we have calculated 8.33. 8.33. 8.33. So from there, I'm going to get here it is 120 minutes. This is your shaper machining time calculation. Clear, everybody? Hope you understand, all of you. Thank you, Rani. Thank you very much. Right. Now, understanding the problem is the key of the solution. Understanding the problem is the key of the solution. Okay. Now, have a look on this problem. So, based on the data, you try to plot the diagram. From the diagram, it would be very useful to you to solve the question. Remembering the formula, number of strokes per minute. So, number of strokes per minute is equal to cutting speed into L by 1 plus Q. From there, you will get number of strokes. Now, number of strokes per minute. Now, if you substitute here B by F into a number of strokes per minute, so that you are going to get your machining time that we have solved over here. So, 120 minutes you are going to get. Clear, everybody? Hope you understand. Now, let us go for the next question, guys. Yeah, have a look on this question. It is related to shaper only. So, just now we have solved now. So, similar to that one. Please have a look on that. Have a look on that. So, by previous question, hope you anybody can solve this question. Please place answers in the chat box, live chat box. What's your answer? Right. Now, in shaping process, the number of double strokes per minute is 30. Number of double strokes per minute is 30. Okay. And quick return ratio is 0.6. If the length of the stroke is 250 mm, the average cutting velocity in meters per minute is. The average cutting velocity for meters per minute is. You have to calculate. So, what is given in the problem? Number of double strokes. So, yeah, guys, here if you number of double strokes in the shaper means it is a one return stroke plus one forward stroke plus one return stroke considered as a one double stroke. Don't consider double stroke mention it is multiplied with the 2. Don't do that. Okay. So, one double stroke means I'll write that. One double stroke is equal to one forward stroke plus one reverse stroke. One forward stroke, that means cutting stroke. In the forward direction only, in the shaper, forward direction only cutting takes place. In the return direction, it is going to be ideal. So, in forward direction, cutting speed is less, and in the return stroke is cutting speed is more. In the in the forward stroke, time is less. In the return stroke, time is more. Time is more. In the return stroke, time is less. Okay, right, like that. So, in forward stroke, one forward stroke plus one reverse stroke. One reverse stroke. Yes, guys. One forward stroke plus one reverse stroke is equal to one double stroke. That is why here they simply mentioned that number of strokes is equal to 30. They mentioned, guys. Okay. Double stroke means we have to consider it as a single. Double stroke, when we call it as, it is mentioned that one forward stroke plus one return stroke is considered as a one double stroke. So, number of strokes per minute is given as NS equal to 30. Now, quick return ratio, Q is equal to 0.6. Okay. Now, length of the stroke is given equal to 250 mm. Now, what they ask you to calculate, guys? They ask you to calculate cutting velocity. So, cutting velocity we have to calculate. Clear, everybody? Yes, guys. Now, let us go to solve this question in a simple way. So, now as we know that number of strokes per minute, let me write full form. Number of strokes per minute. Oh my God, 1 minute. Number of strokes per minute that we have seen NS is equal to, we have seen that VC into 1000 is divided by L into 1 plus Q na. Just now we have solved. Yes, guys. Oh my God, not this. Right. But number of strokes is given. How much number of strokes? Here we require cutting velocity. Now, cutting velocity is equal to, here I can write it is NS into L into 1 plus Q 1 plus Q is divided by 1000. Yes, guys? Right. From there, number of strokes are 30 into length of the job is, length of stroke how much given? Length of stroke is 250. Length of stroke is 250 into 1 plus 0.6 is divided by 1000, right? From there, I'm going to get, it is, 12 meters per minute. 12 meters per minute you are going to get. So, from the number of strokes, you will be able to calculate, 12 meters per minute. Clear, everybody? Hope you understand the solution. Okay, from the number of strokes, we can calculate cutting velocity in the shaper. Right, guys? Right. Now, let us go for have a look on this question. We just shift our talk onto milling. A slot of, have a look on this question in 1 minute. I'll give you 1 minute time. Right. Now, let me go for solve this question. So, a slot of 25 mm deep to be cut through workpiece 200 mm long with the help of high speed steel face cutter whose diameter is 150 mm and it has a 10 teeth. The cutting velocity is 50 meters per minute and feed is 0.25 mm per teeth per revolution. Find the table feed in meters per minute and total cutter travel and time required for the machining the slot. So, these are the three things we are supposed to find out. Clear, everybody? Okay. Now, let us go for solving this. What is the given data? First, you write given data and then we'll go for that. Right. What is that? So, a slot of 25 mm deep. Depth of the slot is, so depth of cut D is equal to, it is 25 mm. Okay. Now, a workpiece of length of workpiece, that is equal to L equal to, length of workpiece, small L will take small L is equal to, it is 200 mm. Yes, guys. Next, with the help of high speed steel cutter whose diameter of the cutter, dia of cutter D is equal to how much, guys? 150 mm. Okay, and it has a teeth, number of teeth on cutter, Z is equal to, it is 10. Number of teeth on cutter is 10. Now, cutting velocity is, cutting speed or cutting velocity both are same, that is 50 meters per minute. Yes, guys. Okay, and the feed is FT. Feed per tooth is given na, FT, that is 0.25 mm per teeth per revolution. Isn't it, guys? Clear, everybody? Okay. Now, let us go for what they ask you to first, table feed in mm per minute. Table feed in mm per minute. First question. Table feed in mm per minute we have to calculate. Okay. Now, I'll select table feed FM, that is equal to, it is FT into number of teeth into N. FT into number of teeth into N. We don't know N. So, now check the, if you check the units, it is feed per tooth, mm per tooth per revolution. Number of tooth, 2 tooth will get cancelled, revolution per revolution will get cancelled, so that you will get mm per minute. Okay. Yeah, thank you very much. Thank you all. Right. Now, let us calculate. We don't know N. RPM of the tool we don't know, na? RPM of the tool, we don't know, right? Next is RPM of the tool, we can calculate from the cutting speed. Okay, what is the cutting velocity? Cutting velocity is given as how much, guys? Cutting velocity is given as 50 meters per minute. 50 meters per minute. 50 meters per minute. From there, n equal to, it is 1000 into Vc is divided by pi into d. Now diameter of the cutter, how much diameter of the cutter? Diameter of the cutter is given 150 mm. Okay, right. Now let us substitute all. 1000 into 50 is divided by pi into 150, so that you are going to get your RPM 106.1 RPM. 106.1 RPM you are going to get. Now substitute all the values. Feet per tooth, feet per tooth, feet per tooth is 0.25 mm per revolution. 0.25, and number of teeth Z. Number of teeth Z is 10 into, it is 106.1, such that your table feed is equal to 265.25 mm per minute you are going to get. Okay, 255 mm per minute you are going to get. Okay, thank you very much, thank you all, thank you Chandrababu sir, and Ajay and Nirmala, everybody, thank you very much. Okay, right. Right, next is right, now have a look on this. Right, we have found the first one. Next, what we have to find? Total tool travel. Okay, tool travel is equal to, next second question, tool travel. Tool travel is equal to, it is L, capital L, length of the job plus approach plus overrun plus compulsory approach. Okay, compulsory approach, AP1. But in the problem, they didn't mention approach and also overrun. That is why your length of the travel L plus AP1. So length of the job is given in the problem now. Length of the job is how much, guys? Length of the job is 200. Now we have to calculate that AP1. Okay, so here it is AP1. Here it is AP1. Okay, from there, so here L is equal to 200 plus AP1. Okay, now AP1 for this milling operation, we gave you the formula na? So what is that? AP1 is equal to, it is D into D minus D under root. It is a slot milling now. It is a slot milling. Okay, yeah, thank you. Thank you very much. Thank you Shantakumar, and thank you Sampath. Thank you very much all. Thank you for listening and thank you for watching. Right, now depth of cut is 25 into diameter of the cutter is 150 minus 25 under root. From there, I am going to get my TAM is equal, approach, compulsory approach is 55.90 mm. 90 mm. Now, length of the tool travel. Length of tool travel is equal to, it is gonna be a L plus AP1. So that is equal to, it is 200 plus 55.90. Such that it is 255.90 mm is the total tool length travel. This is the second question is finished. Okay, now let us go for third question. What the third question they ask? Time required to machine the slot. Time required to machine the slot. Right. So now third question. Time required to machine the slot. Time required to machine slot, that is equal to, it is obviously it is L by F dot N. So I can write it is L by directly Fm. Okay, so length of the job is 255.90 is divided by, it is 265.55. So your time for machining is equal to, it is 0.964 minutes. This is what your answer. Okay, guys. Hope you understand, all of you. Okay, thank you very much. Okay, so here I gave you the formula that table feed in mm per minute is equal to this relation you are supposed to remember. Okay, Now if you check the units, units is given as mm per tooth per revolution, mm per tooth per revolution. Okay, thank you Chandrababu sir, thank you very much. Okay, right. Now here it is ft, mm per tooth per revolution. So tooth and revolution will get cancelled, so that you are going to get mm per minute. Clear everybody? Right. Hope you understand. Let us go for the next question. Yeah. Yeah, take a look on this. Have a look on this question. We will go forward. Well, welcome back to the session. Thank you guys. Have you read the question? Right. See that a tube is orthogonally machined in a lathe to reduce its length under the following conditions. Okay. Outside diameter of the tube is 100 mm. Inside diameter of the tube is 96 mm. What happened? Inside diameter of the tube is 96 mm. RPM of the workpiece is 120. Now longitudinal feed is 0.54 mm per revolution. Chip thickness ratio is 0.3. Tangential force is, that is FC, 800 newtons. Axial force, that means feed force. Here it is a feed force. Feed force is given as, axial force 600 newtons. What we have to calculate? So we have to calculate chip velocity in mm per minute and total power consumption in kilowatts for this machining operation. Okay, right guys. Now let us go for solve this question. Okay, right. Let me write given data. What is given data? Inside outside diameter d naught is equal to, it is 100 mm. D naught is equal to 100 mm. Now di inside diameter is equal to, it is 96 mm. Okay. Now n is equal to how much gave? 120 RPM. Next is longitudinal feed. F is equal to, yes guys, F is equal to 0. How much? 0.54 mm per revolution. Next, what next given? Chip thickness ratio. R is equal to 0.3. That is equal to, it is T1 by T2 na. So T1 by T2 is equal to 0.3 is given. Next, FC is given. Cutting force is given, that is 800 newtons. And feed force. F feed force, 1 minute. Feed force, that means axial force, is equal to 600 newtons. Now what we have to find? We have to find, so power equal to, and also chip flow velocity, that is VF, we have to find. So these are the two things we are supposed to find. Clear everybody guys? Okay. Now we know that power formula is equal to, it is FC into VC. FC into VC. But FC we know, but we don't know the VC. Now VF. So we have a relation that, what is that? R equal to VF by VC. R equal to VF by VC and R equal to 0.3. Now, if we are able to find out that cutting velocity for this question, so that the entire problem will going to be solved, na? Yes guys, right? Now, let us go for solve this question. Let us go and solve this question. Right. Now, cutting velocity. Cutting velocity or cutting speed, VC is equal to, it is how much? Pi d n by 1000. Pi d n by 1000. Okay. Now pi into d. So d, what d you are supposed to consider here? Here we have a 2 d's na, d initial and d final. But do remember guys, always do remember, keep in mind that whichever the maximum diameter that is exposed for the tool, that is exposed for the machining, that thing you are supposed to consider as a, that thing you have to consider as a diameter while calculating the speed, cutting speed. Clear everybody? So which one is maximum? 100. Okay, right? Outside diameter is a maximum, right? From there, here it is a 100 into RPM, 120 I guess. Let me check 120 or not. RPM of the tool, yeah, 120 RPM. Here it is RPM guys, revolution per minute, right? 120 is divided by 1000, such that I am going to get my cutting velocity is 37.69 meters per minute. Okay, why I have divided this 1000? I just wanted to convert my cutting velocity into meters per minute. Clear everybody? Hope you understand. Now let us calculate that first. VF is equal, VF by VR equal to R, that is equal to 0.3. From there I require chip flow velocity, right? Chip velocity is equal to, it is how much it is? 0.3 into VC. Yes, now 0.3 into VC, 37.69, such that you are going to get, it is 11.30 meters per minute. 11.30 meters per minute you are going to get. Clear everybody guys? Okay, now let us go for calculating the next power. Second one is power P is equal to cutting force into cutting velocity. Okay, now cutting force is 800 newtons into, you know, it is how much it is? 37.69 meters per minute. Okay, and this is in newtons. Okay, now Newton meter is a joule per minute you will get. So now I just divide this 800 into 37.69 is divided by, you know, 60. So that what happened? Newton meter per second. Okay, such that it is going to be what happened guys? Joule per second. So joule per second I can write it as watts. Okay, now if I do that, I am going to get units in watts, that is 502.23 watts I am going to get. But in the problem they ask you to calculate that power in kilowatts. That is why we just divide that fellow with 1000. So if I divide that 1000, 0.50 kilowatts you are going to get your power for this cutting operation. Clear everybody guys? Okay, yeah, hope you understand the solution. Now let us go for, next question. Yeah, next question. Have a look on this question guys in 1 minute. Welcome back guys. Let me read the question. Okay, what is that? A 25 by 5 centimeter cast iron surface is to be a 25 by oh my god, a 25 by 5 centimeter cast iron surface is to be face milled milling machine with a cutter having diameter of 10 centimeter diameter of milling cutter and having 16 teeth for the cutting speed, and feed speed is given 50 meters per minute and feed is 5 centimeter per minute respectively. Determine the milling time, RPM and feed for tooth. They are asking you to calculate. Okay, What we have to calculate? RPM of the cutter and feed per tooth, FT, we have to calculate, and also milling time also we have to calculate. Okay. So now what is the job here, guys? It is a 20 by 5 centimeters. 20 by 5 centimeters. Okay. Now for that case, what happened now? I just give and write the data. So jobs workpiece size is equal to, it is 20 by 5 centimeter. Okay, such that it is gonna be a 200 by 50 mm. Yes. So because I just converted it all dimensions into mm. Okay. So yeah, thank you Sampath Kumar, thank you very much for your nice compliment. Okay, I'll keep rocking, I'll keep posting the things, I'll keep feeding you and make you to crack the GATE exam. Okay, right. Now, so this is what the dimensions of the workpiece. Now I'll just draw the briefly dimensions of the workpiece. This is what the dimension. What is that? 200 mm length, 200 mm length, and width is 50 mm. Width is 50 mm. Clear, everybody? Right. Now here 200 by 5 centimeters. Now next, milling machine. Cutter having diameter. Diameter of the cutter is given. Dia of cutter D is equal to, it is how much? 10 centimeter. Now I just converted this into 100 mm. Now it is converted into 100 mm. Having teeth, number of teeth on the cutter. Number of teeth on cutter, so that we consider it as a Z is equal to 10, I guess, right? Yeah, 10 number of cutters. Oh my God, 16, having 16, it is not 10, 16. All right, 16 teeth. Cutting speed is given. So cutting speed is given, that is equal to 50 meters per minute. 50 meters per minute. Right? Now feed is given. Feed is given, it is 5 centimeter per minute. Now I just converted this into 50 mm per minute. I just converted this into 15 mm per minute. Clear, everybody, guys? Okay. This is what the data given. What we have to find? Milling time we have to find first, and RPM of the cutter and feed per tooth. Feed per tooth you have to calculate. So now let us go for solving the question. RPM. So from the cutting velocity we can get na. So cutting velocity we see equal to, it is pi d n by 1000. Pi d n by 1000. I require RPM, that is equal to speed. So 1000 into Vc is divided by pi into d, right? From there, what is Vc? Vc given in the problem 50 meters per minute. 50 meters per minute. And d also will see. What is d? 100 mm. Okay, d is 100 mm. Now 1000 into, oh my God, it is 50 or 60? Forgot, 50 only. Yeah, it is 100. Is divided by pi into 100. From there, I am going to get my RPM of the tool, 160 RPM I am going to get. 160 RPM I am going to get. Yes, guys. So first one is over. Next, second one is feed per tooth we have to find. Feed per tooth, that is FT, we have to find. Okay. As we know that table speed or table feed, that is equal to FM is equal to, it is FT into N into Z. Yes, guys, FT into N into Z. From there we require FT na. So FT is equal to, here FM is divided by N into Z, right? Now FM is how much? Table feed is given na. Table feed is given 50. So here what is that? Feed centimeter per minute, that is table feed, that is FM it is, okay, 50, right? Now it is gonna be a 50 is divided by 160 into 16. So RPM is 160 and number of teeth on the cutter is Z is equal to 16, right? From there I am going to get feed per tooth is equal to, it is 0.0196. 0.0196 mm per tooth per revolution. Okay, so like this you are supposed to find out. Clear everybody guys? Okay, next is milling time. Milling time we have to find. Milling time is equal to, it is gonna be a L by Fn again. L by Fn again. Okay, now let's decide that L. Okay, L equal to, it is length of the job plus approach plus overrun plus it is AP1, compulsory approach. But here approach and overrun is not given in the problem, isn't it guys? Okay, approach and overrun is not given in the problem. So look at in the problem, there will be a no approach and overrun. Yes, so and it is a phase milling. So that is why here, you know, these two things are not given. Now from my approach and overrun is going to be, see, my length of the job is equal to L plus AP1. Now let me calculate AP1. AP1 is equal to, it is you know, half is divided by D in D minus D square minus W square under root. D square minus W square under root. Okay, so now half into, it is gonna be a D 150 minus and D square again 150 square minus W square. So what is W square? W square is a 50 square, width of the workpiece, width of the workpiece. Now it is gonna be a 50 square. From there I am going to get my AP1. D is how much guys? Diameter of the, oh my god, diameter is 100 only. We have substituted 100 square. From there I can get, it is you know, half into 100 minus 86.60. 86.60. Now from here I may get, it is 6.7. Okay, now my length of the tool travel is equal to, length of the job is how much guys? Length of the job is 200. Length of the job is 200, right? Now from there it is gonna be a 200 plus, you know, 6.7 is equal to, it is 206.7 mm. Okay, now L we know, F we know, and substitute in that. Okay, now milling time is equal to, milling time is equal to, it is L by F dot N, or I can write it is L by directly Fm. Okay, from there it is 206.7. Yeah, 206.7 is divided by, it is gonna be a feed velocity is how much? 50. From there I can get my milling time is equal to 4.137 minutes. Okay, 137 minutes I am going to get. Okay, clear everybody guys? Okay, hope you understand the question. Okay, have a look on the question. I just summarize, right? So this block is going to be milling machine, machined on a milling machine. Cutter radius is, cutter diameter is given. How many teeth on the cutter is also given. Number of teeth also given, and speed is given, and also feed, table feed also given. Now we have to find out that feed per tooth, RPM, and milling time. Okay, for feed per tooth, so RPM we can calculate like this. Feed per tooth, table feed is equal to feed per tooth into RPM into number of teeth on the cutter. From there I can get FT, so that I can get FT, feed per tooth is equal to 0.0196 mm per tooth per revolution. Okay, now milling time is equal to L by Fn. Now I have decided L. L equal to length of the job plus approach length of the tool travel and overrun of tool travel, and also compulsory approach, right? But approach and overrun not mentioned in the problem. That is why we neglected that. And L plus approach 1. And approach 1 is going to be this much. And I just added that. Next is L plus L divided by Fm table feed, so that you are going to get your milling time is equal to 4.137 minutes. Okay, hope you understand the solution. Thank you all of you. Now let us go for the next question guys. Right, have a look on this question. Now, hope you listen the question, read the question. Here, let me solve this question, guys. Right. Now, a T slot is to be cut in a cast iron slab shown in figure. Estimate the machining time. Taking cutting speed is 25 meters per minute. Feed is 0.25 mm per revolution, and dia of the cutter of channel milling is 80 mm. Okay. So, by using this, we are supposed to calculate the machining time required for producing this slot. Here, you will be able to see the slot. What is the slot? It is a T slot, right, guys? First, we have to produce the slot, a 20 mm slot, 20 mm width, and 35 mm depth slot. We have to supposed to machining. Okay, are you getting my point? So here, see guys, here what I'm trying to tell you, here T slot is going to be produced with a milling machine. This is what, okay. Now, right, now here, see, first we have to produce this slot. First, we have to produce this slot. So, what is this slot? This is a 20 mm depth. Yes, this is a 20 mm depth, and it is 15 mm. So, 15 mm depth and 20 mm width of the slot we have to produce. For that, we have to calculate the machining time, isn't it? So, 20 mm depth and 35 mm depth and 20 mm width of the slot machining time we have to calculate. After that, what is the machining time for this? After that, machining time for 60 mm wide, 20 mm depth of the slot machining time we have to calculate. Okay, guys. Hello, Prasanna. Thank you. Thank you very much. Keep listening. Keep watching. Thank you. Thank you very much. Right. Now, see that first we'll calculate machining time for the depth of this slot. After that, this T slot will calculate. Okay, right. Now, what is given in the problem? So, estimate the machining time. Cutting speed is given now. Right. Let me write cutting speed. Cutting speed is given is equal to, it is how much, guys? 25 meters per minute. 25 meters per minute. And feed is equal to, it is 0.25 mm per revolution. Okay. Now, dia of the cutter is given, it is 80 mm. 80 mm, right? Now, first we'll calculate the slot machining time for this slot. Okay, right. Next, go for that. Right. Now, first I'll write calculate machining time. Calculate machining time for 35 mm depth. Oh my God, 1 minute. 35 mm depth and 20 mm width. 20 mm width of slot. Okay. Now, time machining time for first one will take T1. Okay. Now, T1 is equal to, it is L by F dot N. Okay. Right. Now, here what is L? What is L? Here L is equal to length of the job. So, this slot 35 mm depth and 20 mm width of the slot in a 260 mm length we have to produce. In a 260 mm length we have to produce. Yes, guys. Clear, everybody? Yes? Yeah. In this length we have to approach. Okay. Now, let us go for solving this. Now, first we'll calculate N. N we don't know na. N equal to, it is 1000 into VC is divided by pi into D. So, diameter of the cutter is given na. Diameter of the cutter is given 80 mm. 80. So pi d. So from here 1000 into VC is I guess 25. VC, yeah, 25. So 25 is divided by pi into d is how much? D is 80. D is 80. So that I am going to get my RPM is equal to 100 RPM I am going to get. Now feed is also given, na? Feed is also given, that is 0.25 mm per revolution. Okay. So now feed is equal to 0.25 mm per revolution. Okay, right. Now let us decide that L. L is equal to, it is length of the job, 1 minute. Right. Now length of the job plus approach plus OR plus approach 1. So approach and OR is not given, that is why L plus AP1. Now my AP1 is equal to, it is small d into d minus d under root. Isn't it, guys? Okay. Now from here it is gonna be a 35 into diameter of the workpiece cutter is 80 minus 35. Okay, depth of cut. So depth of cut is 35 now. Here depth of cut is 35. That is what I have considered like that. Okay, right. Now from here if I solve that, I am going to get, it is 39.68. 39.68 mm. Okay, right. Now here length of the job is 260. Length of the job is 260. Length of the job is 260. Approach length is 39.68. Okay. Now here L equal to, it is L plus AP1, that is equal to, it is 260 plus 39.68, such that you are going to get, it is approximately 300 mm. Okay. Now T1 is equal to, it is L by F dot N. Now L is equal to 300 and F is equal to how much F? F is equal to 0.25. and N is equal to 100. Now if you solve this, then you are going to get, it is 12 minutes you are going to get. 12 minutes you are going to get. Okay, that is for what? Thank you very much, Ravindra. Right. Now here what I am trying to explain you, up to here we have calculated only machining time required for this slot. Okay. Yeah, thank you, Samir, thank you. So here we have calculated machining time for producing this slot only. Now we have to produce this slot, 60 mm slot towards the 260 mm length, okay, with a face mill cutter. Okay. Now here what happened now? So what is the depth of cut here? Depth of cut here is 20 and diameter of the cutter is 60, T slot cutter. Okay, right. Now let us go for calculating the machining time for T slot. Machining time for T slot. Machining time for T slot with dimension how much? 60, sorry, 20 by 60, right? It is 20 by 60. So width is 60 and 20 mm slot. Okay, with a diameter of with the tool diameter 60, with tool dia 60 mm. Okay, now let me explain you that how it is 60. See guys, now we have produced this slot. Now what happened now? So a 60 mm slot has to be taken. So 60 mm slot has to be taken. Slot mill cutter. Okay, this cutter will take. Okay, and it is having dimensions like this, and it has to move towards like this. Clear, everybody, guys? It has to move towards like this. Now 60 mm diameter of the tool, 20 mm depth, it has to machine towards 260 mm. For that we have to calculate the machining time. Clear, everybody? Right. Now machining time, again our basic formula, what is that? L by Fn. Machining time or the T slot. Machining time for T slot. So that is T2 is equal to, it is again L by F dot N. L by F dot N. So here F is similar same. Okay. So here F is similar same. Now N equal to, it is 1000 V is divided by pi into D. Now here 1000 into, it is 25. Cutting speed is 25 only, na? Yeah. So now pi into D. How much D we have to take? How much D we have to take? Now the D is we have to take. So this is a cutter diameter 60 mm. Okay. So it has to move towards the slot like that. Okay. For that purpose, okay, our diameter of the cutter is 60 mm. So from there, I'll get my RPM is equal to 133 RPM. Now, it is a slot milling. It is a slot milling, right? It is a slot milling. T-slot milling operation. So, face milling. So, what is the approach length of the tool travel? Approach length of the tool travel is equal to, here let me decide that, L equal to length of the job plus AP1. Here AP1 is equal to diameter by 2. AP1 is equal to diameter by 2. Now diameter is 60 is divided by 2, that is equal to 30. Now length of the job is equal to, it is length of the job 260 plus 30. So that it is gonna be a 290 mm. Okay, it is gonna be a 290 mm. Now we know that N and we know that F and we have decided L also. Now let us go for machining time. So T2 we'll consider T2. Why? Because it is a T-slot cutter. Now it is gonna be a 290 na. So 290 is divided by 0.25 into 133 RPM. Yes guys, from there it is gonna be a 8.7 minutes. 8.7 minutes. Clear everybody? Okay. Yeah, thank you very much ma'am, Rajita ma'am, Sridevi ma'am, thank you very much. Okay, right. Now from here, so what we have to find? What they have asked actually. See guys, so this is a slot which we have been seen that, see, so first we have calculated the machining time for producing this slot. So 20 mm width and 35 mm depth of the slot machining time we have calculated. From there, we produce this sleeve slot in a 260 mm. So here I have taken two machining times. Machining time for producing the 20 mm width of the slot, machining time for producing the 60 mm width of the slot, so that we will get the total T slot on the given machining. So total T slot on the given workpiece, right? Now for calculating the machining time 20 mm slot, I have considered T1, and calculating the machining time for the 60 mm width of the slot is T2. Now T1 plus T2, so that I'll get total machining time for this producing T slot. Clear everybody? Okay, right. Now here T1 plus T2 is equal to your total machining time. What is the T1 here? So T1 we got that 12 minutes, and T2 we got that 8.7 minutes. Okay, total machining time for producing T slot. Total machining time for producing T slot, that is equal to T equal to, it is T1 plus T2. Now T1 is equal to 12 minutes and this fellow is 8.7, that is equal to, it is 20.7 minutes is, oh my god, 1 minute guys. It is 20.7 minutes will be your answer. Hope you understand, all of you guys. Okay. Now this if you engage these kind of typical questions, so that you will get most of the times they ask you to calculate that table speed and also RPM, cutting speed. Okay, and also thank you Jivan, thank you very much. Okay, and machining time calculations. So here I gave you the two parts, but they ask you one part in the. So if you go engage and encounter these kind of typical questions, so that it will be very easy to you to solve the small things. Okay, that is why I collected some typical questions for this session. All right, guys, hope you understand and enjoying the session. Now let us go for the next question, guys. Yeah, have a look on this question. In 1 minute, I'll be back. Yeah, welcome guys, welcome back to the session. Now have a look on this. It is another question for drilling, from the drilling. Okay, right. Now let me read the question. A drilling operation is to be performed with a 12.7 mm diameter of the drill bit. So drilling operation is going to be performed in a workpiece with a diameter of the drill bit is 12.7 mm. The hole is blind hole. The hole is blind hole and at a depth of 60 mm. Okay, blind hole means it is not completely produced onto the workpiece. It is produced up to certain depth and we will just leave there only. Okay, right. That is what that blind hole. The cutting speed is 25 meters per minute and feed is 0.3 mm per revolution. Determine the time required for drilling and also metal removal rate in mm cube per minute. Okay, clear everybody guys? Okay, now let me explain you that what is so first we'll write given data and then we'll segregate that. Dia of the drill bit, dia of drill hole or drill bit, dia of drill hole D is equal to, it is 12.7 mm. Yes guys. Okay, next is blind hole. So depth of hole, depth of hole, so is equal to 60 mm. Depth of hole is equal to 60 mm and cutting speed VC is equal to 25 meters per minute. Okay, now feed is equal to, it is 0.3 mm per revolution. Okay, now for producing this hole, how much time it will take, that we are supposed to calculate. Now let me give you some example for the this particular blind hole. See that this is a workpiece. This is a workpiece. Okay. Now I'm going to produce a hole on here. Now, so blind hole means up to certain depth we produce the hole. Okay. What depth they said? So up to 60 mm depth we have produced the hole. Okay. Blind hole means it is not completely produced throughout the thickness. Okay. Now, if the hole is produced like this, if the hole is produced throughout the thickness, if it is the thickness of the workpiece, okay, so if it is completely throughout the thickness, it is come under through hole. Okay, if it is not produced to the throughout the thickness, then it is considered as a blind hole. So here I'll write that what is blind hole, what is this one. Okay, now this fellow we'll consider it as a blind hole, blind hole. And this fellow we consider it as a through hole, through hole. All right. Yes, guys, through hole. All right. Now, for producing this blind hole, how much time it will take? The time we are supposed to calculate. Clear, everybody, guys? Now, let us go for time for hole. Time required for drill hole. Time required for drill hole. time required for drill hole. That is equal to, again it is L by F dot N. Again it is L by F dot N. So we don't know the N, we don't know the L. Okay. Now let us calculate that L. L is equal to length of drill bit travel. Length of drill travel or drill bit travel. Alright. From there, again it is length of the job, sorry, thickness of the job plus approach plus overrun plus compulsory approach. Okay, compulsory approach. From here, so thickness, here it is thickness, I'll write clearly. It is a thickness. See guys. So actually we have to consider this thickness. So this much thickness the drill bit is going to be travel. So while it is drilling, if it is considered as a tool travel, it is going to be travel along the thickness now. Right? That is why thickness we have to consider. But here do remember, it is a blind hole. Tool will travel up to only this much distance only. Tool will travel up to this much distance only. So in place of thickness, I'll substitute 60. Right? Now here approach and overrun is not given now, but compulsory approach is there. So this is 60 plus compulsory approach. So compulsory approach is 0.3D for blind hole. For blind hole. Have remember this? So for blind hole it is 0.3D. For through hole it is 0.5D. Yes guys. Okay. Now here it is gonna be I'll write here 0.3 into it is 12.7. Okay. We'll keep like this same. Yes. Now here let us calculate that length of that. So it is 60 plus 0.3 into 12.7. From there I can get it is 63.81 mm. 81 mm. Now we don't know the N. We don't know the N. Now let us calculate that N. N from the cutting speed we can calculate now. That's right. Now from there N equal to it is 1000 V into pi d. 1000 V into pi d. Now here 1000 into, so what is the cutting speed is given in the problem? Cutting speed is given in the problem is 25. 25. Okay. Now here 25 and pi into diameter of the drill bit is 12.7. From there I can go to and I'll get RPM of 626.59. 620. Oh my god. 626.29 RPM I am going to get. Now I know L, I know N and F I know, so that I can get time required for drill hole na. Time required for drill hole na. Yes guys. Okay. Right. Now let us go for time required for drill hole. Time required for drill hole. Time required for drill hole, that is L by F dot N. Okay. Now here it is F guys. Oh my god. Let me erase this. It is equal to, it is L by F dot N. Now L is equal to, how much we have calculated L? L is 63.81. 63.81 and F is F is going to be 0.3 into 269.59. 269.59. Okay. Now from here you are going to get it is 0.33 minutes. And you are going to get it is in seconds, 20.36 seconds you are going to get for drilling this hole. Time required for drill this particular hole is this much. Clear everybody guys? Hope you understand. Now let us second question, not yet finish this question. So they ask you that metal removal rate also. How can we calculate that metal removal rate in drilling operation? That means during producing this drill hole, how much amount of the metal is going to be removed per minute? That is what we have to calculate guys. Okay. Right. Now let me go for that. right? Metal removal rate in drilling. Now let me take another ink. Metal removal rate in milling. Okay. Oh my God, not milling, drilling. Drilling. So that is gonna be a is equal to, it is going to be what happened, guys? It is area pi by 4 d square into n into f, right? So now pi by 4 into d square is 12.7 square into n is 269.59 into f is 0.3. From there, I am going to get my metal removal rate 23812.33 mm cube per minute. So if I convert this into meters, so that 23.81 meter cube per minute. So this much amount of the material is going to be removed. Metal removal rate is nothing but area into speed into feed. So that you are going to get metal removal rate in drilling operation. Area is mm square, na? It is mm square. It is mm per revolution. See that it is mm square and it is mm per revolution per minute. Revolution per minute. It is mm per revolution. Revolution will get cancelled. Revolution will get cancelled. Mm cube per minute it will come. Clear, everybody, guys? Okay, right? You can check your units also like that. Right? Hope you understand, all of you. Now let us go for another question. Yeah, have a look on this question, guys. In a minute, I'll be back. Yes, guys, I hope you have seen this question. Okay, let me explain you this question. A hole and shaft have basic size of 25 mm. A hole and shaft having basic size of 25 mm diameter or to have a clearance fit. So hole and shaft both are having clearance fit. That means both. Suppose if you take this is shaft and this is a hole, the hole and shaft is going to be rotated easily inside. The shaft is going to be rotated inside the hole is very easily because it is a clearance fit. Clear, everybody, guys? Okay. Next, clearance fit with a maximum clearance of 0.02 mm, minimum clearance of 0.01 mm, and the hole tolerance is to be 1.5 times of the shaft tolerances. Determine the limits for the both hole and shaft using hole based system and using shaft based system. Okay, guys? Okay, what they said that it is a clearance fit, and also the relation between the maximum clearance and minimum clearance is given. Maximum and minimum clearance is given. Now we have to find what is that. They gave the one relation. The tolerance on the shaft, the tolerance on the shaft, the tolerance on the hole is going to be given that. See that the tolerance, the hole tolerance is 1.5 times than the shaft tolerance. Determine the limits of the both hole and shaft using a hole based system, using a shaft based system. Hope you understand the question, and for more understanding and for more getting the data, I'll just give you the diagram so that you will be able to find out that. Okay, right. Now first I'll draw the hole. Hole. All right. Now hole tolerances is this is what hole. I'll consider it as a hole. Now let me draw the shaft. let me draw the shaft. This is what my shaft. This is a shaft tolerances. Okay. Now they said that clearance speed. That is why the gap between the shaft and hole is there. Okay. This is what the shaft. But what they said, the clearance speed, maximum clearance is 0.02 mm. What is the maximum clearance? Maximum clearance is you know, maximum hole of the diameter. That means upper limit of the hole minus lower limit of the shaft. Upper limit of the hole minus lower limit of the shaft. This is what maximum clearance. So maximum clearance is given. Maximum clearance is given. How much it is? 0.02 mm. 0.02 mm. Isn't it, guys? Right. Next, minimum clearance. Lower limit of the hole minus upper limit of the shaft. This is given that minimum clearance. This is how much it is? Minimum clearance is 0.01. 0.01 mm. Yes, students, understood? So based on the data, I'm just plotting the diagram, and every data, whatever the data given in the problem, I'm just inserting in the diagram so that it will be very easy to you to solve the problem. Okay, try to understand. Right. Now, maximum clearance is given, minimum clearance is given. Right. I don't know the tolerance on the shaft. This is a tolerance zone, na? This is a tolerance zone. So this dotted line and this thick line of the shaft is the tolerance on the shaft. And this dotted red line and this dotted line is the, tolerance on the hole. But both we don't know. But one relation they gave. What is that relation? The hole tolerances is to be 1.5 times of the shaft tolerances. Hole tolerances is to be 1.5 times of the shaft tolerances. So here if I consider that this fellow is x, that I don't know, I'm taking it as x. Okay. Now I'm going to take hole tolerances are I'm taking it as y. What they are giving? The tolerances are the hole tolerances is to be 1.5 times of the shaft tolerances. Can I write like this? Y equal to, it is 1.5 times of the x. Yes, guys, that is what they gave, na? The hole tolerances is to be 1.5 times of the shaft tolerances. X is the shaft tolerances. So that 1.5 times of the x is equal to hole tolerances. That is what I substituted, I presented over here. Okay. Now what we have to find? Limits of both two. So upper limit of the hole, lower limit of the hole, upper limit of the shaft and lower limit of the shaft by using hole based system, by using shaft based system. Clear, everybody? If you are aware of shaft based system and hole based system, so that it would be very, very easy to solve the problem. Okay. So what is a hole based system? In hole based system, the lower limit of the hole is basic size. That is equal to, it is lower limit of the hole is, lower deviation is 0. For hole based system, lower deviation is 0. Isn't it, guys? Right? So lower limit of the hole is equal to basic size. Lower limit of the hole equal to basic size. What is the basic size? 25 mm. So this is 25 mm. Where? For hole based system. For hole based system, lower limit of the hole is basic size. Okay. Now from here, I just wanted to find out that x and also y. Then only it is possible to find out the upper limit of the hole, lower limit of the hole, lower limit of the shaft and upper limit of the shaft can be able to find out. Clear, everybody? Right. Now, can I write like this, guys? Y plus 0.01 plus x equal to 0.20, because maximum clearance is equal to x plus 0.10 plus y. Isn't it, guys? Now, from there, let me write that. Here, y plus, oh my God. Here, y plus and 0.01 plus and x is equal to 0. How much? 0.02. 0.02 mm, isn't it, guys? But we know that y equal to 1.5x na. Now, in place of that, 1.5x plus 0.01 plus x is equal to 0.02. Now, x equal to, I can write it is 0.04. If you calculate that, you are going to get x equal to 0.04 mm. Now, y equal to, it is 1.5 times of the x na, right? Now, from here it is 1.5 into 0.04 such that you are going to get it is 0.006, mm, isn't it, guys? Okay, now fine. Here it is 00, guys. I'm sorry. .004, so that you are going to get it is 0.006. Okay. Yeah. Thank you. Thank you. Thank you very much, Raju. Thank you very much. Yeah. Yeah. Thank you, Rajesh. Thank you, Rajesh. Balu also. Thank you very much. Yeah. Thank you. Thank you very much. Thank you. Thank you, Rajesh. Thank you very much. Thank you, Rajesh Chaudhary and Raju and Balaji, Balu and everybody. Thank you. Everybody, thank you. Okay, right. Now we got know that what is that x value we have found and y value we have found. What is x value? It is 0.006 and it is gonna be a 0.004. Right. From there, let us go for decide the whole base system first. Okay, right. First whole base system. Whole base system. Whole base system. In whole base system, so lower limit of the whole is equal to basic size. Lower limit of whole. Lower limit of whole is equal to basic size. Lower limit of the whole is equal to basic size. Okay, right. Now lower limit of the size. What is the basic size? Lower limit of the whole of the basic size 25.00. Now upper limit of the whole. Upper limit of whole. Upper limit of whole, that is equal to lower limit plus tolerances on upper limit, lower limit of the whole, plus tolerances on the whole. Okay, right. So now lower limit is 25.00 and the tolerance on the whole 0.06, so that it is going to be a 25.0.006 mm is the whole dimensions for, yeah. Okay, next is upper limit of the shaft. Upper limit of shaft. Upper limit of shaft. Okay, now guys, see that I know that lower limit of the whole in the whole base system is 25. For that I add tolerances so that I can get upper limit of the whole, isn't it, guys? Okay. Now if I want upper limit of the shaft, then what happen? Lower limit of the whole minus 0.01. Lower limit of the whole minus 0.01. Then you will get upper limit. Once upper limit of the shaft you will get, if you deduct 0.04, so that you are going to get lower limit of the shaft, isn't it? Right. Now let us go for solving that. Okay. Now if I want upper limit of the shaft, lower limit of the whole minus minimum clearance. Minimum clearance. It is a minimum clearance, na? Right. Right. Upper limit of the shaft is equal to lower limit of whole minus minimum clearance. Minimum clearance. Okay. So what is the lower limit of the whole? 25.00 minus minimum clearance is, it is 0.01. Okay. From there I can get my lower limit of the shaft. My lower limit of the shaft is equal to, 1 minute, upper limit of the shaft. Upper limit of the shaft is equal to 24.99 mm I am going to get. Isn't it, guys? Okay. Now I require lower limit of the shaft. Now lower limit of the shaft. Lower limit of shaft is equal to here upper limit of shaft minus tolerance on shaft. Upper limit of shaft minus tolerances on shaft. Tolerances on shaft. Alright. Now upper limit of the shaft is 24.99. Just now we have calculated now. Upper limit of the shaft 24.99. And what is the tolerances on the shaft? Tolerance on the shaft is 0.004. Okay. Now 0.004 minus it is 0.004. From there, I am going to get my lower limit of the shaft is equal to, it is 24.986. 24.986 mm I am going to get. Yes, guys. Next is, this is what the hole base system. In hole base system, what happened now? Lower limit of the hole is, yeah. Thank you, Surendra, and thank you very much. Thank you very much. Right now, so in a hole base system, we'll fix that lower limit of the hole is constant. Lower limit of the hole is constant. Yes, guys. Now, in this case, using shaft base system, what happened now? Upper limit of the hole, upper limit of the shaft is going to be constant. Upper limit of the shaft is going to be constant. That is equal to basic size. That is equal to basic size. Okay, right. Now, let me go for the first. We have solved that. So, hole base system. Hole base system. Now, let us go for shaft base system. Second case is shaft base system. In shaft base system, okay, upper limit of shaft is equal to basic size. Upper limit of shaft is equal to basic size. Upper limit of shaft is equal to basic size. Now it is equal to, right. Now here basic size is 25.00. Yes, guys, 25.00. Okay. Yeah. Now let us go for calculating the lower limit of the shaft. Lower limit of shaft is equal to, it is upper limit of the shaft minus tolerances. Upper limit of shaft minus tolerances. Tolerances on shaft. Tolerances on shaft. Yes, guys. Upper limit is 25.00. It is point. Okay. Minus tolerances is 0.004. From there, I am going to get it is 24.996 mm you are going to get. Clear, everybody, guys? Yeah. Thank you, Chano. Thank you very much. Okay, right. Next is go for upper limit of hole. Oh my God, lower limit first we'll calculate. Right. Now see, guys, I'll just go back to the diagram once. Yeah, in shaft based system, what happened now? So this limit is equal to 25.00, right? So if I want lower limit of the shaft, 25 minus 0.04, so that you are going to get your lower limit of the shaft. Next, in this case, if I want lower limit of the hole, then what happened? Upper limit of the shaft plus 0.01, so that I can get lower limit of the hole in shaft based system. Do remember, guys? So do remember, guys, what happened now? In hole based system, lower limit of the hole is basic size. In shaft based system, higher limit of the shaft is basic size. Okay, so based on that, the dimensions are going to be changed. Okay, so keep observing that. Now let us go for lower limit of hole. Lower limit of hole. Lower limit of hole is equal to upper limit of shaft plus minimum clearance. Minimum clearance. Yes, guys. Okay. Now I just go back to the diagram. Yeah. So if I want lower limit of the hole, upper limit of the shaft plus 0.01. This is the minimum clearance, na? So that I am going to get that one. Right. Now upper limit of the shaft, that is equal to 25.00 plus minimum clearance 0.010. That is what you are going to get. It is 25.01 mm. Next is upper limit of the hole. Upper limit of hole. Upper limit of hole. So that is equal to lower limit of hole plus tolerances. Lower limit of hole. Lower limit of hole plus tolerances. Lower limit of hole plus tolerances. What is lower limit of the hole? It is 25.01. Now tolerances on hole is equal to 0.006. Okay. From there, I am going to get it is 25 point, so 0.16 mm. Okay. Like that, you are supposed to calculate your dimensions. Clear, everybody, guys? So hope you understand, all of you. Okay. Now, based on that hole based system and shaft based system, so I gave you the differences. Please have a look on that. In hole based system, lower limit of the hole equal to basic size, right? Now, in shaft based system, upper limit of the shaft equal to basic size. Based on that, you are supposed to calculate your dimensions. Clear, everybody? Right. Now, let's go for the next question. Right. Have a look on this question, guys. I'll give you 1 minute time and have a look on this question. Right. Now, let me go for solving this question. So, what is the question here? In an EDM process using RC relaxation circuit, 12 mm diameter through hole is made in a steel plate of 50 mm thickness using a graphite tool and kerosene as a dielectric fluid. Dielectric fluid. All right. Now, from here, assume discharge time is to be negligible. Machining carried out under the following conditions. Machining carried out under the following conditions. Now, resistance is 40 ohms and capacitance is 20 microfarad and supply voltage is 220 volts and discharge voltage is 110 volts. Find the average power input. So, find the average power input. Clear, everybody, guys? So, now we have to find average power input. Okay, what is the given data we are supposed to write? Okay, now let me write that. So resistance R equal to, it is 40 ohms. Next, capacitance is equal to, it is 20 microfarad, and from here I can write it is 20 into 10 to the power of minus 6 Fahrenheit. Next is supply voltage. So V naught is equal to, supply voltage is equal to 220 volts and discharge voltage VD is equal to 110 volts. Okay. Now what we have to find, guys? Average power input in a EDM process. Okay. Now here average heat input is equal to, what is that? Average power input. Average power input is equal to energy per spark. Energy per spark is divided by cycle time. Cycle time, that is equal to TC. Average, energy per spark or divided by cycle time, so that you are going to get your, thank you, Shantakumar. Now you are going to get cycle time of TC. Okay. Now let decide that energy for spark. Energy for spark is equal to, half C VD square. That is half into C is capacitance is 20 this one, okay, right. 20 into 10 to the power of minus 6 into 110 volts, okay. Now cycle time is equal to, cycle time is equal to TC, it is RC into ln of, supply voltage divided by supply voltage minus, discharge voltage, okay. Now R is equal to 40 and this fellow is 20 into 10 to the power of minus 6 into ln of V0 is, V0 is 220 and this will be divided by 220 minus 110. So that if you substitute these two values over there, average input you are going to get, okay. Average power input is equal to, it is 1 by 2 into 20 into 10 to the power of minus 6 CV d square na, yeah, VD square it is. So here it is 110 square is divided by cycle time is equal to 40 into 10 to the power of minus 6 ln of, it is 220 is divided by 110, okay. Now if you solve this, you are going to get average power input, 0.22 kilowatts you are going to get, okay. So now here you need to find out the, thank you Sampath, thank you very much. So here you need to remember the energy for spark formula and cycle time. Cycle time can be given as resistance into capacitance into ln of V0 by, that means supply voltage by supply voltage minus discharge voltage, you are going to get cycle time. Now this is the energy per spark is equal to half into CV d square, you are going to get that much. Hope you understand, all of you. Thank you very much guys. Now let us go for next question. Yeah, have a look on this question from CNC. Yeah, welcome guys. Have a look on this question. That is, a DC servo motor is coupled to a lead screw which drives the table of CNC machine tool. What is that? A DC servo motor is coupled to lead screw. We have discussed na DC motor, pulse generator, DC motor and lead screw and then work table is placed over there, okay. Now a DC servo motor is coupled to lead screw which drives the table of CNC machine tool. A digital encoder mounted on the another end of the screw emits 500 pulses per revolution. 500 pulses per revolution. That means pulse generator. Next, the pitch 5 mm per revolution. The motor rotates 600 rpm. Then determine table speed, basic length unit, and also frequency of pulses transmitted by the encoder we have to find. These are the three terminology we are supposed to find, okay, right. For that purpose, first you write that given data. Pitch is given how much guys? Pitch is equal to, it is 5 mm, and during solving the problems I said that consider pitch equal to 5 mm per revolution, okay. Next, N, motor rotates at the speed of 600 rpm. 600 rpm. Now what they said, first we have to calculate that table speed na, table speed, right. Now let us go for first question, that is table speed V is equal to, it is N into P. Now what is N? 600 into 5 mm per revolution, okay. Now it is gonna be a V is equal to, you are going to get, it is 3000 mm per minute. 3000 mm per minute you are going to get. Alright guys. So from there you are going to get, it is 3000 is divided by 60 mm per second. Mm per second. Clear everybody? So you are going to get, it is 50 mm per second. Table speed is equal to 50 mm per second. Yes guys, right? Yeah, thank you Alone Creations. Thank you very much for your kind complement. Okay, right. Next is stable speed, BLU. Next is basic length unit, BLU we have to find. BLU you can write it is pitch by pulse per revolution, pitch by pulses per revolution. Now pitch equal to 5 and pulse per revolution is equal to how much it is? It is 500 pulses. Okay, so that you are going to get it is 1 by 100, 1 by 100 mm per pulse, mm per pulse. Okay, from there I can write it is 0.10 micrometer. Micrometer is a basic length unit. Clear, everybody? Okay, right. Next is third question is frequency we have to find. Okay, now here we know the relation that basic length unit into frequency is equal to speed. Okay, now basic unit length is 1 by 100, that is 10 micrometer into frequency we don't know, and table speed we know that 5 mm per second, 5 mm per second. Now here F equal to it is 5 divided by, so 1 by 100 mm per mm. So your frequency is equal to, it is gonna be a, so speed is 50 na, 50 mm per second. Now from here you are going to get 5000 hertzes. 5000 hertzes are going to be get. Okay, thank you. Who's that? SD or something. Okay, thank you very much guys. Okay, frequency like that we can get. Now let us go for the next question. Have a look on this question, matching question. From the list given below, choose the most appropriate set of heat treatment process and corresponding process characteristics. Okay, now here one side they gave the processes, heat treatment process, and another side is required characteristics they gave. Okay, from there we are supposed to calculate, match the following. What is tempering? So tempering is, what is the definition of the tempering? Why tempering is going to be done? What is the characteristic of tempering? We are supposed to see. Now see, tempering. Austenite is converted into bainite. Is it related to tempering? No. Austenite is converted into martensite. It is also not related to tempering. Tempering is nothing but, tempering is the process which is used for reduce the brittleness and hardness and import the ductility on the hardened component. Right, that is what come under tempering. Next, so here tempering, cementite is converted into globular structure. No. Next, tempering, both hardness and brittleness are reduced. Yes. So in tempering process, what happened now? So after hardening, do remember guys, very good statement that, so hardening must be followed by the tempering, because hardening is nothing but heating a component to certain degree temperature and quench it in a water. Once you quench it in water, martensite structure is produced, that is a brittle structure and also hard nature. So because of the quenching, some scalar formation produced on the workpiece surface. Right. For removing the scalar formation, for removing the brittleness of the component, we just go for the tempering. So hardening must be followed by the tempering. Tempering is a process which is used for reducing the hardness and also reducing the brittleness of the component, hardened component. So P equal to, so P is related to fourth statement. Next, austempering. What is austempering? So austempering, austenite is converted into bainite, is come under austenite. Okay, right. Now here austempering is nothing but, austempering is converting the austenite into bainite. Next, Mott tempering. Mott tempering is nothing but austenite is converted into martensite. So R equal to 2. So austempering means austenite converted into bainite. Mott tempering means austenite is converted into martensite, is come under this one. So here P4 and Q1 and R2. So your answer is C. So for solving this question, you should be very aware about that your particular heat treatment processes, Okay, Hope you understand. Okay, thank you very much, all of you guys. I have covered all the topics, all the chapters, and typical questions for today. And last for the 3 days, I have solved all the manufacturing questions which are typical, which we have not covered in our regular offline classes. I collected some typical questions so that these typical questions definitely help you and boost your confidence levels, so that you follow these kind of instructions and these kind of problems. Definitely your gate rank is going to be increase. Okay, so now let us go for announcing the new batch of let me announce new batch. Right now, live online batch. We have a online, offline, and hybrid classroom, guys. Online, offline, and hybrid classroom. Okay. Now here what happened now? So live online class January 3rd will open. That will start for ECE EEE will start signal system subject. Next for mechanical and civil will start engineering mechanics. Right. For CS will start with a TOC. And the same another batch will start on Saturday, January 7th. Networks for ECE EEE and instrumentation, and FM and hydraulics for civil and mechanical. Okay. Now for CS is a operating system. For contacting online batch, you may contact with these numbers. You may take a snapshot. Next. For classroom new batch, that means offline. I said just now we have online, offline, and also hybrid batch. Hybrid batch means it's a combination of online and offline. 70% is a offline, and 30% is a online. Okay, right. Now classroom batch. Classroom batch will start on January 8th, 2023, Sunday. For ECE, EEE, and instrumentation, digital will start. Mechanical and civil will start SOM, and CS will start a signal. Now, if you want to join the classroom batch, you may contact Jayanagar IMS GATE Academy, number 41, 4th floor, South End Road, Basavanagudi, and Bangalore is a landmark is above the Adiswar Market, and this is what the address. Now you may contact through the telephone also by using these numbers. All right, guys. Now let us go for hybrid classroom. Hybrid classroom will operate in Vijayawada. So now here hybrid batch, the day start will January 3rd, and for signals and system, ECE and EEE instrumentation. For mechanical, we will start engineering mechanics. Okay. Now Saturday. On Saturday, January 8th, 2023, we will start control system for ECE, EEE, and instrumentation. And for mechanical, we will start FM and hydraulics. And now the Vijayawada address is 40-1-59, 3rd floor, BOI building, that is Bank of India building, opposite Modern Supermarket, Ben Circle, Vijayawada. You may contact through the telephone also, or else you may visit the address. Okay. So thank you all of you for listening, patient listening to the session. And I hope last 3 sessions, manufacturing part 1, part 2, part 3, you have enjoyed. And I have kept all good questions and typical questions I have solved in easy methods. If you follow these kind of rules and regulations and approach of the questions, so that definitely your confidence level increases. And I hope you are preparing well, and I'm very all the best to your preparation, and God bless you for your examination. Okay, thank you all of you, thank you very much.